Alright, in this video I'm going to talk about total differentials. That is the very first topic in chapter 8. So we finally move on to new chapter, and in this video I'm going to talk about the first topic in that chapter. So in order to introduce differentials, let me go back to partial derivative. So whenever we have function f depending on two variables, uh, so two variables x and y influence function f. And the way to see how does this function respond to change in variables. So the basic idea of partial derivative was, although we have two different channels, we can block one of them. So regarding y as a constant, so regarding x as the only variable of this function, and we examine how does function change over x. Okay, so when x changes a little bit, and while keeping other variable y constant, we examine how does function change over x. That is the partial derivative with respect to x. Because the function depends on two variables, we can examine the same thing over variable y. So now we block this channel. So treating x as a constant, so regarding y as the only variable of this function, and we can examine how does function respond to change in y. That is a partial derivative with respect to y. Right? So using this technique, we can do several comparative static analysis in economic models. For example, we have a demand curve and one supply curve. So that is an example of market model. But in contrast with the previous market model, where we take a look at two separate markets at the same time, that this model describes just one market. So this is a partial equilibrium analysis. So this curve denotes the demand for one product, and this supply curve denotes the supply curve for the same product. Okay, and we have several parameters here, A, B, C, D, and A and C are y-intercepts of demand and supply respectively, and B and D are slope of these two curves respectively. All right, and then suppose that in this model, I want to see the impact of tax on the equilibrium price. So suppose that tax T is imposed on the consumers, all right? So that changes the demand curve. More specifically, it changes the slope of the demand curve, all right? So it increases the slope of the demand as much as 1 plus T. Okay, so here T stands for the tax rate. So if we draw this demand and supply, right? So here we have a demand curve and supply curve. Putting quantity on the vertical axis and putting price in the horizontal axis. And you can see that if T is imposed on demand curve, then demand curve becomes steeper. So we have another intersection right here. And if we want to see that equilibrium effect of tax on price, then I may set QD equal to QS. So QD equal to QS, and then solving for P. Then I can obtain explicit form of the function, function of price. So A plus C over B 1 plus T plus D, I guess. All right, so here A, B, C, D are positive, is positive constant. So if T increases, so as if the higher tax is imposed on consumer, we can anticipate price will decrease because an increase in T amplifies the size of the denominator. So as a result, equilibrium price will decrease like this. Okay, so this figure visualizes the impact of tax T on equilibrium price. All right, so that is a kind of partial derivative analysis because we're regarding A, C, B, D, other variables constant. So keeping these four parameters constant, we just increase the size of T, and then we just saw that how does equilibrium price respond to change in T. That is a So that captures the idea of a partial derivative. So in this way, we can do several comparative static analysis in economic models. But the question is, so whenever we have an explicit form of a demand curve and supply curve, then we can find explicit form of a price and expressing that as a function of several variables, and then we can do some partial derivative analysis. But what if we have limited information about quantity demanded? So QD is no longer this linear function, but just some arbitrary function f of p and t. So the only thing we know about this quantity demanded is, so quantity demanded is given by arbitrary function and is a decreasing function of p and decreasing function of t, meaning that as price increases, quantity demanded decreases, and as tax rate increases, so some tax is imposed on some specific product, the demand for that product will decrease. That is quite a natural assumption. So we just know that this function is decreasing with respect to each argument. So we have a limited information because we don't know the exact form of the demand function. Okay. But nevertheless, the way to find the equilibrium price is the same as before. So we set the quantity demanded equal to quantity supply. So we have this characteristic equation. And then let's suppose that, so let's do partial derivative analysis. So here we have several parameters, P, T, and C, and then we increase T, okay, a little bit, keeping the other variables constant. But it doesn't make any sense because, we just saw that price also varies with the tax. So price is also a function of T. So the partial derivative means we just increase t, treating other variables as constant, but that is inadequate in this example. Okay, so whenever we have a general function model, partial derivative is going to be inappropriate, so inadequate. So we can't change just a one variable, in this example. So can do such a partial derivative analysis. So whenever we encounter this kind of model, now we have to open these two channels at the same time. So we have to consider total variation of function. Partial derivative bears on just the partial variation of this function because we block the other channel, right? So in case of partial derivative with respect to y, we block this channel, so we did not consider change in function f due to change in x. X was a constant. But whenever we increase t or decrease t, so whenever we change t, we can easily see that prices also changes, right? So whenever we analyze this function with the partial derivative, we have some problem. Okay, so now we have to think about how to consider total variation. So, okay, so how to define total variation of a function in case of two variables. Okay, so that is a kind of brief introduction of total differential. Now we have to think about a different approach for comparative static analysis. And to understand the total differential, let me first go back to single variable function. So we have a f of x is given by, so we have f of x given by x squared plus 1. Now we can easily compute the derivative using differentiation rule. So 1 constant goes away and x squared becomes 2x because of the power rule, right? So the derivative is denoted by f prime of x. So that highlights the fact that this derivative is a derived function from f of x. So if we plug in 1 for x, then we obtain value of 2. So this function, so derivative, so one function we can derive from the original function f of x gives us the slope of the tangent line at each point. So if we plug in 1, then we obtain 2, and this number 2 stands for the slope of the tangent line at point 1. So suppose that this is the graph of x squared plus 1. So at point 1, the function is instantaneously increasing at the rate of 2 at point A. And so this is the tangent. And then the slope of this tangent is given by the derivative. So 2 indicates the slope of this tangent. Okay? So that is one way to understand the derivative. And another way to understand the derivative is, remember the derivative is also denoted by dy over dx. Okay? And I already illustrated the meaning of dx, that is a differential of x. So differential for x. Okay? So it stands for marginal change in x, so infinitesimal or very tiny change in x. Okay, so here we have dy over dx. Okay, and then let me read this dy. So differential for y divided by differential for dx. Differential for x. Okay, then I can multiply both sides by dy. Okay. So after substitution, so after plugging 1 for x, then I can rewrite this dy equals 2 times dx. Okay, so this is a total differential so this is a differential of y. Now that is given by 2, the derivative, the value of the derivative at point 1 times differential for x. Right? So now going back to this figure, if we interpret this equation, so dy equals 2 times dx, but dx is the change in x, right? So that's going to be the length of this line segment AC, okay? And then if we multiply by 2, then dy is going to be the height of this triangle. So the length of the line segment C and D, okay? And if we compare that with the function's value, actually, the total variation of function when x changes from a to c. So when x increases by dx, how much does function increase by? The variation of the function is going to be, this one. And if we compare with dy, okay, differential of y, there is some error, right? There is some error between dy and actual variation of function. Okay, so dy can be interpreted as the linear approximation of the function when x changes by dx. Okay, so when x changes marginally, so when we consider some substantial change in x, so when dx is large, so the dy makes some difference from the actual variation of function. But on the other hand, when dx is small, this dy will be very close to actual variation of function, right? So we can use that dy as a proxy for the actual variation of the function. Okay, so that is a differential. So the derivative gives us some linear relationship between two differentials dx and dy. Okay, and the derivative can be defined as the ratio of these two differentials. Okay, so once again, the differential gives us linear approximation of function when x changes, okay, in case of a single variable. Right, so this formula and this figure summarize the idea that the derivative is the limit of the rate of change as the change in x goes to 0. Right, so dy, so the corresponding differential dy can be seen as linear approximation of delta f, the actual variation of function. Okay, So that gives us some idea of total variation. How do we have to treat? So how do we have to deal with the total variation of a function when function depends on several variables? Okay. So now if we consider function depending on two variables x and y, and if we compute the partial derivative, now the partial with respect to x becomes 2x because now we consider 2y as a constant, right? And then partial with respect to y gives me 2 because now x squared is a constant, okay? But these two partial derivatives pertain to a partial variation of function. So for instance, f sub x indicates instantaneous rate of change of z with respect to marginal change in x, or differential dx, okay, with the variable y held constant. So 2x can be thought of as the linear approximation. So the linear approximation of functions variation, so partial variation, when just the x changes, okay? And 2 also can be thought of as a linear approximation of partial variation of function f when y changes only. In fact, when y changes only, the function will change at the rate of 2. If y changes a little bit, say dy, okay, then the function will decrease or increase depending on the sign of dy. So the function will increase or decrease as much as 2 times dy. Okay, so the partial derivative also can be thought of as a linear approximation. All right. Now, if we open the two channels, okay, so here x and y influence output z, okay. Now we open these two channels, now considering the total derivative or total differential or total variation of the function. And then the idea comes from linearity, because now how do we add these two channels, because a differential has a linearity. So we just compute partial variation due to just a change in one variable. So because function f depends on two variables, we have two partial variations, variation due to dx and variation due to dy. And how do we treat these two numbers? We just add them up because of linearity. If we have two variables x1, x2, and suppose that there is a linear relationship between these two, then its outcome is going to be x1 plus x2. Okay. So function originally depends on two variables. So we have two partial variation due to change in each variable. And how do we treat these two variations? We just add them up because differential has a linear relationship between linear relationship with dx and dy. So the total differential, that is a proxy of total variation, is defined as the sum of two partial variations. So if we understand this, and the remaining topics are just a piece of cake. So one thing you have to notice is, as opposed to partial derivative, the total derivative allows all variables to change. So now we allow x changes because we consider partial variation due to dx. We also allow variable y to change, right? Because we take into account variation due to dy as well. All right, so that is a total variation, or total differential, or total derivative. Okay, so total differential can be thought of as a linear approximation of total variation. Okay, so when x and y change marginally, okay, then we obtain two partial variations from each change. And because differential has a linear relationship with dx and dy, so we just add them up. Okay, so that is a basic idea of total differential. Right, so formally, total differential of f is defined as df is partial variation, so the partial derivative with respect to x times dx, plus partial derivative with respect to y times, oh, this is a typo, it should be dy, okay? And then the differential is defined as the sum of these two variations. So of course, in case of a single variable function, so if function depends on just x, then we don't have the second term. So, the concept of total derivative or total differential will coincide with partial derivative. Okay. All right. Then, with this idea in hand, let me compute. So let me show you how to compute the total differential. This is a piece of cake. That is just a repeated application of what we have studied so far. So the previous differentiation rules and the chain rule and partial derivative. Okay. So for the first example, now f is given by function of x1 and x2. Then how do we compute df? That is f sub 1 dx1, partial variation due to change in x1, and f sub 2 dx2, variation due to dx2. So f sub 1 is going to be a, because bx2 is a constant, times dx1. And f sub 2, now a sub x1, ax1 is a constant, so f sub 2 becomes b dx2. Right? For the second, now total differential is, now depends on x and y. So total differential is going to be sum of these two. Right? And f sub x, the partial with respect to x, 2x plus y, because we have additional y, because we have xy term. Now regarding y as a constant, its derivative is going to be just y. And similarly, f sub y is a 3y squared, x squared is a constant, and y cubed becomes a 3y squared, and xy becomes x, and dy. Okay, and finally, we have another function depending on x1 and x2. So df is, f sub 1 dx1 and f sub 2 dx2. So f sub 1, now x2 to the 1 minus alpha is a constant. So we just take this part and take the derivative using the power rule. Then that gives me alpha x1 alpha minus 1 x2 1 minus alpha times dx1, and partial with respect to x2. Now x1 to the alpha is a constant, right? So we take this part and take the derivative. So x1 alpha, leave it alone, there's a constant, and then 1 minus alpha comes up front, and we take 1 away from the power, so the new power becomes negative alpha. So dx2. All right. So once you understand the why total differential should be defined as the sum of the partial variations, the way to compute total differential is just a piece of cake. It's just a repeated exercise. All right, and then the basic rules. These rules are the same as before. So whenever we have a constant, so, if f of x and y is given by constant, then its total differential should be 0 because there is a no variable here, right? And then f of x and y now is given by c x to the power m. So now, it does not depend on y, only depends on x, right? Then originally df is f sub x dx, f sub y dy, but because function is independent of y, so we don't have this second term, so we just can consider f sub x dx. So f sub x is c n x to the power n minus 1 due to the power, and then we multiply by dx. And then now function f is given by x plus minus y, so f sub x becomes 1, and f sub y, so depending on the sign, it's going to be plus minus 1. So we have this. Okay? When f is given by x times y, f sub x becomes y, and f sub y becomes x. So we have this. Finally, f is given by x over y. So x over y can be thought of as x times 1 over y, right? So we can decouple x from 1 over y. So the derivative with respect to x, partial with respect to x is now 1 over y is a constant. So 1 over y dx. And then derivative partial with respect to y, right? Now x is a constant. So leave x alone. And 1 over y is y to the power negative 1. So applying the power, negative 1 power, we bring out the power and subtract 1 away from the power. Right? And then I can rewrite this. So 1 over y dx and minus x over y squared. Because y to the power negative 2 is the 1 over y squared. Alright, so we don't have to treat these rules as a separate one, because the basic idea comes from the definition of a total differential. So regarding this, the expression in the parenthesis as a function of f, as a function of x and y, and then we just apply the definition, and then we can obtain these rules in a very simple way. All right, we have 3 more exercises, and let me do just one. So let me do this one. Okay, it looks the most complicated. So f is given by function of x1 and x2. So df is f sub 1 dx1, f sub 2 dx2. Now f sub 1. So now regarding x2 as a constant, we take the derivative. And let me first rewrite this. So I can rewrite this, so distributing 2x1 squared to each term. So x1 divided by 2x1 squared, and x2 divided by 2x1 squared. Right? Then I can rewrite the first term as 1 over 2x1. And then rewrite the second term as so 1/2 x2 x1 to the power negative 2. Okay, and rewrite the first term as well. 1/2 x1 to the power negative 1. Okay. Then f sub 1. Okay, now regarding x2 as a constant, and its partial is going to be negative 1/2 x1 to the power negative 2, and then negative x1 to the power negative 3 x2, because if we multiply 1/2 and the power, we have negative 1, and then we have to take 1 away from the power, so the power is going to be negative 3. Okay, then x2 is a constant, so I just left it alone. Right, and then multiply by dx1, and f2. So, this guy goes away because there's no x2 term. And 1 half x1 squared negative, so x1 to the power negative 2, now that is a constant. So I'm going to leave it alone. And then x2's derivative, that is just 1. Okay, so we have this. All right, so this is the way to compute total differential, and the way to understand the total differential as the sum of two partial variations. Okay, and then the key idea was, we can think of the derivative as the ratio of dy, so dy over dx, and from that we can see some linear relationship between dx and dy. So the derivative specifies a linear relationship between these two differentials. So it can be thought of as a linear approximation of actual variation of a function. Okay. So when x changes a lot, there is some gap between actual variation and dy. So dy cannot be seen as a good approximation of the actual variation, but when dx is small, it gives us some good proxy for actual variation. Okay. Hope you find this video useful, and I will see you in the next video then.